So today I will start new course of classical mechanics, and I briefly talk about its introduction and how this classical mechanics or the is different than Newtonian mechanics. And in the first section of this classical mechanics, I will talk about variational principle and Lagrangian formulation of mechanics. This section starts with variational principle and Lagrangian formulation of mechanics. I'm not talking about today this what is variational principle and what is Lagrangian formulation, but I will just briefly introduce this. So all of us are familiar with the Newtonian mechanics. And what is Newtonian mechanics, or what we do in Newtonian mechanics? Mx, it is a vector quantity. It is written in bold letters, and it is equal to F. It is again bold. It's a vector quantity. This force is also a vector quantity, and this is acceleration. Mass into acceleration is nothing but is equal to force, net force acting on the system, and it is the equation of motion. And what do we do? What is our purpose? Our purpose in this equation is to find out the value of x, or x as a function of time. How x evolves with time, how particle moves, and what is its trajectory, what happens to the particle with time. That's what we do. And if we solve this equation for harmonic oscillator, then for harmonic oscillator this is equal to minus kx. And the solution, when we got its solution, what is its solution? It's x is equal to a naught sine kx. This is the solution of it, or it may be in the form of cos. That's what we are getting. So or it is x naught, not k. Is it kx or no? Sorry, omega t. It is a naught sine of omega t. This is the solution which we are getting. So how system evolve with time? That's what we are getting out of it when we solve this equation. And the important thing is that these quantities are vector quantities. These quantities are vector quantities, and when we do little algebra, we will arrive at here. That's our purpose. So if we try to look at it, this problem of harmonic oscillator is like this. It's a mass attached to it, and if set into oscillation, it is like this. And if it is undamped oscillator, then its wave function looks like this. It is the shape of it. It is the time evolution along this axis, and this is the x-axis. If you plot it, so this looks like this. Means I am able to predict the trajectory of the particle. What is the future of the particle, and where the particle will go in the future. So Starting with this, I am arriving at this conclusion. That's the purpose. So this is all about it. And this development of mechanics using this equation is known as what? Is known as vectorial formulation of Newtonian mechanics. Vectorial formulation of Newtonian mechanics. This is Newtonian mechanics, and this is a vector formulation. We have to deal with the vectors, but it is little bit difficult to deal with the vectors. If we have possibility that if we can replace these vectors by some scalars, then we are more comfortable, right? So people developed a new formulation of mechanics. People developed new formulation of mechanics. Mechanics means what they did in place of force. They start talking about in terms of energy, right? And when we start talking in terms of energy, and what is energy? Energy means kinetic energy and the potential energy. Energy means it is the kinetic energy and potential energy. So people start talking in terms of energy. Energy means kinetic and the potential both, right? And means we are incorporating energy into our formulation, and this formulation is known as, in which we will start talking in terms of energy, this is known as scalar formulation of mechanics. This formulation is known as scalar formulation of mechanics. So at UG level you started with the vector formulation, but now we are starting with the scalar formulation. And in this formulation we will talk about Lagrangian and Hamiltonian formulation. We will talk about Lagrangian and Hamiltonian formulation. It's Lagrangian Hamiltonian formulation. And another advantage of this Lagrangian and Hamiltonian formulation, say we started with the Lagrangian and Hamiltonian, it's a scalar formulation of mechanics, and it makes our life much more simple. And another advantage of this Lagrangian and Hamiltonian formulation is also helpful in quantum mechanics. Advantage of this is also helpful in where? Helpful in the development of quantum mechanics also. And we are not worried about vectors and directions. We only include the energy terms. What are the energy terms involved in it? We have to worry about the energy terms. And energy terms including kinetic energy and the potential energy. So once these terms are known to us, We start doing little algebra and again arrive at the equation of motion. As we have seen for the harmonic oscillator, x is equal to a sin omega t. Now purpose is again same. We can also predict the behavior or the trajectory of the particle or the assembly of particle. But we have to start with the scalar quantity, and that scalar quantity is energy. And that's why this formulation, Lagrangian and the Hamiltonian formulation, is very interesting and makes our life more simple. That is the advantage of it. So it's easy to deal with the scalars rather than a vector. So Lagrangian formulation, we will talk in terms of Lagrangian, and Lagrangian is nothing but T minus B. T is what? T is the kinetic energy. Total kinetic energy of the system, and V is the potential energy. V is the potential energy, and H is the Hamiltonian, and it is the sum of all the kinetic energy terms, whether it is the kinetic energy and the potential energy. So in this course we will enjoy this new formulation, right? So that's all for today's lecture.